Okay, so this is the final section of Chapter 4. We'll call this Lecture 4 Part 8, which corresponds to Section 4.9 of your text, remembering that we skipped Section 4.6. All right, and so in this section, we talk about antiderivatives. So it's the undoing of differentiation. So, they are definitely way useful in not only in scientific problems, but economics problems, business problems, natural and social sciences problems, just about everywhere. So a physicist who knows the velocity of a particle might wish to know its position at a given time. An engineer who can measure the variable rate at which water is leaking from a tank wants to know the amount of water leaked over a certain amount of time. A biologist who knows the rate at which a bacteria population is increasing might want to deduce what the size of the population will be at some future time. In each case, the problem is to find a function big F whose derivative is a known function little f. So if such a function big F exists, it's called the antiderivative of f. In other words, if we have a function, we want to know, so suppose I give you this. Suppose I give you f of x, all right, just like I've been doing all along. So the question is, the derivative of what function equals to f of x? So we call this big F of x, okay? So the derivative of big F of x is equal to f of x. And this time I give you this, I give you little f of x, and you are tasked with finding what is big F of x, all right? Then big F of x is called the antiderivative of little f of x. Little f of x is the derivative of big F of x. All right, so that's all we're pursuing here. So, and that's the only way you can do it. Just answer the question. The derivative of what gives you f of x? Okay, so there's a definition. Okay, so a function big F is called an antiderivative of f on an interval I if the derivative of big F is equal to f of x for all x in I. All right, so the antiderivatives are confined to a certain interval, not necessarily the entire x-axis. All right. So, for instance, if f of x is equal to x squared, then we can kind of deduce that the derivative of x cubed over 3, so if we differentiate this function, we'll get x squared. All right? So in this case, the antiderivative of x squared is x cubed over 3. And you can just run the power rule for differentiation in reverse. Okay, that's all we're doing. We're doing differentiation in reverse. All right, so think about it. There is a function big G of x, which is equal to x cubed over 3 plus 100. And if you take the derivative of this function, which is not the same as the previous solution, the big F of x, then its derivative also is equal to x squared. So we have two functions, f and g, that are antiderivatives of f. All right? So in fact, we have an infinite number of antiderivatives of f. So any function big H of x, which is equal to x cubed over 3 plus some constant, is an antiderivative of f. So are there any other antiderivatives besides this family of functions? Okay, so to answer the question, we use the mean value theorem. And the mean value theorem was used to prove that if two functions have identical derivatives on any interval, then they must differ by a constant. All right, so we deduced that from the generalization of the mean value theorem. Okay. So if f and g are any two antiderivatives, then they must differ by a constant. Okay, so that comes from a corollary to the mean value theorem. So the antiderivative is big F of x plus c. Okay. So the antiderivative of x squared then would be more formally written as x cubed over 3 plus a constant, and that's a family of functions. And here they are sketched. So you can see a selection of some functions. All of these functions are antiderivatives of x squared. And basically the constant is just a vertical shift of the function of x cubed over 3. All right, so we can find any derivatives of other functions. So for instance, the derivative of what is sine x? Probably what? The antiderivative would be minus cosine x. plus a constant. And the way you would verify that is just take the derivative of this function and you'll get back sine x. The antiderivative of 1 over x would be the natural log of x plus a constant. To convince yourself, take the derivative of the natural log of x plus a constant, you'll get 1 over x. If n is not -1, the antiderivative of x to the n would be something like this, right? So what's the derivative of x to the n minus 1 over n minus 1? Well, if we were to differentiate this, plus a constant, we're at the constant. So if we were to differentiate this function using the power rule for differentiation, that would just be x to the n. Okay? So that's how it works. Okay. Okay, so, and then they work. What we just did, so we just did that real fast. Okay. So, remember that Theorem 1 tells us that the general antiderivative of f of x is the natural log of the absolute value of x plus c on any interval that does not contain 0. And we use absolute value because we could potentially put negative numbers in for x, for f of x. And so we want to make sure that we don't stick a negative number into the natural log function, because the natural log function is not defined where numbers are negative. Okay, and we can't put 0 in there either. So make sure you understand the restrictions on using this tool. Okay, so so the general antiderivative of 1 over x would be this function, a piecewise defined function, and that's why we can instill using the absolute value. Okay, and we can use the power rule for anti-differentiation for x to the n. And so, yeah, as long as okay, so it's valid as long as n is not 0. Okay. And then here's a table of anti-differentiation formulas. So the antiderivative of a sum of functions the antiderivative operator commutes over a sum of functions. Okay, and then here's the power rule for anti-differentiation. The antiderivative of 1 over x. And the antiderivative of e to the x, of course, is e to the x. The antiderivative of cosine x is sine x. And the antiderivative of sine x is negative cosine x. And you can verify all of these, okay? So the antiderivative of secant x tan x is secant x. And how do you know that? Well, just take the derivative of secant x and you'll get back secant x tan x. And the antiderivative of 1 over the square root of 1 minus x squared is inverse sine x, okay? And I think we did that a while back. So here's some particular antiderivatives. I call these the familiar antiderivatives. Okay, so slide 26. So yeah, antiderivative formulae. Yeah, so they just talk about antidifferentiation. So find all functions g such that g prime is equal to this. So basically you take the antiderivative of the right-hand side. Okay, so remember the rule, replace the radical with its exponential form. So g prime of x is equal to 4 sine x plus 2x to the 4th plus x to the minus 1/2. All right, and so the antiderivative, so we'll call it gx, would equal to minus 4 cosine x plus 2/5 x to the 5th plus, so you add 1 to the exponent, which makes it 1/2, and then divide by the exponent. Okay, and so this would be, and then don't forget your family of functions, so your integration constant. Anti-differentiation constant, I guess we could call it. So that would be your antiderivative for this. And you can check it by taking the derivative of each term in the expression, and you'll get back the original function. All right. Okay, so do they do that on the next slide? Okay, and so here we have, yeah, so here they just replaced, they did the division, and they replaced the, just like we did, they replaced the radicals with exponential formats. Took the antiderivative. Okay, and that's what we got. All right, good. Okay, so we have differential equations. So an equation that involves the derivatives of a function are called differential equations. Don't worry about it. We're not going to go to chapter 9. Okay, so find f if, okay, so this is a differential equation. And what we've got here is, okay, here's your differential equation. We want to find f. And this situation on here, these are called initial conditions, or an initial condition that allows you to compute a specific value of c. So here we have f prime of x is equal to e to the x plus 20 over 1 plus x squared. So the general antiderivative, so again, this looks to be a typo. This should not be f prime of x. This should be f of x is equal to e to the x plus 20 arctan x plus c. Now, we have f of 0 is equal to negative 2. So what you do is if you plug in 0, so f of 0 is equal to e to the 0 plus 20 arctan 0 plus c, and that equals to negative 2. Okay, but arctan 0 is 0, e to the 0 is 1, so c must be negative 3. So solving for c, c is equal to negative 3. So you can make that negative 3 based on the initial condition. All right, so you just solved a differential equation. C is negative 3. Okay. Okay. All right. Find f if f double prime is equal to 12x squared plus 6x minus 4. And then we have two initial conditions. All right. So to do this, and I'm pretty sure there's going to be a web assigned question regarding this, take the antiderivative of f double prime to get the derivative of f, which is 12 times x cubed over 3 plus 6x squared over 2 minus 4x plus your antiderivative constant. And then we take the antiderivative of f prime to get f of x. So f of x is equal to 12 times x to the 4th over 4 times 3, which is 12, plus 6x cubed over 6 minus 4x squared over 2 plus cx plus d, right? And so now we just have to plug in the initial conditions to get c and d. So we have f of 0 is equal to 4. So let me extend the page. So f of 0 is 4. So plugging in 0, we'll have d is equal to 4. And then f of 1 is equal to 1. So if we plug in x equals 1, we'll have 1 plus 1, which is 2. 2 minus 2 is 0. So we'll have c plus d is equal to 1. So c is equal to negative 3. All right. So let me erase this so you can see it. So here they solve just like we did, f prime of x. And so f prime of x begets f of x. Okay, just like we did. And then now you need to solve for c and d. C is negative, d is 4, and c is negative 3, just like we did. Okay. So what else? Okay, therefore the required function f of x is written thusly. Let's this graph thing here. Okay, so if we're given a graph, then we should be able to sketch the graph of the antiderivative. Okay, so this looks interesting. So suppose we're given that f of 0, the antiderivative of a function at 0 is 1, and so we have the point 0, 1. So in which direction should we move our pencil? The direction in which we move our pencil is given at each stage by the derivative f prime of x is equal to f of x. Okay. All right, so how to graph f even if we don't know a formula for f. Okay, all right. So let's see what do we have here. So we want to make a rough sketch of the antiderivative f given that f of 0 is equal to 2. Okay, so here's the function f of x, and we want to sketch the antiderivative of this function. Okay, so how should we proceed? The slope of y equals f of x is equal to f of x. Okay, so between 0 and 1, we would think that the f of x would be a decreasing function, right? Because the derivative of f, big F is negative between 0 and 1. So maybe, perhaps a guess would be something like, okay, so we have f of 0 is equal to 2, right? So there's 2. So we would think that the graph would look like this. And then from 1 to 2, it would be increasing. Then it would go flat at 2. And then from 2 to 3 to 4, it would be a decreasing function, and it would go flat. And then again, it would be an increasing function. Perhaps something like that. Well, no, not quite. Not quite. Let's see. It would have to be. Okay. Well, let's see. Let's move forward and see how the book treats it. Okay. So we start at 0, 2, right? And draw f as an initially decreasing function because little f is below the x-axis. So from 0 to 1, you're decreasing. And then from 1 to 2, you would have to be increasing. And since the derivative of the function is above the x-axis, between 1 and 3, so between 1 and 3, okay, here's 3, we would have to have an increasing function, right, because it's above the x-axis. And at 3, of course, the derivative is 0, so that means we would have to attain a local max at x equals 3. And then from 3 forward, the derivative of the function is below the x-axis, so we have to be a decreasing function. But at x equals 4, we transition from a decreasing function to an increasing function, right, at x equals 4. And so that would tell us that even though the derivative is below the x-axis, that would signify a local minimum of the derivative of a function would translate essentially into an inflection point. So we're not only are we decreasing, but we change concavity. Okay, so let's see how they treat this subject matter. So f of 1 is equal to f of 3. So f has horizontal tangents when x equals 1 and x equals 3. So f is increasing from 1 to 3, so we've deduced that. Okay, fair enough. I'm interested in the point of inflection point. Okay, when f has a local minimum when x equals 1. Okay, so for x greater than 3, f of x is negative. So f is decreasing on 3 to infinity. Yep, that's true. But how is it decreasing? As f of x approaches 0, as x approaches infinity, f becomes flatter and flatter, right? Because the slopes of the tangents become horizontal. All right, that's true. Also, the second derivative of f, which is equal to f prime of x, changes from, oh, okay. So they consider the derivative changes from positive to negative at x equals 2, and from negative to positive at x equals 4. So f has inflection points. Yeah, okay. So, yeah, so the way they considered it is if we look at the tangents to the derivative function, okay, they change from, so the second derivative of the function changes from positive to negative. So the blue arcs are the second derivative of big F. And so whenever you have a change in the second derivative from increasing to decreasing, okay, then x equals 2 denotes an inflection point. And then at x equals 4, the change in the derivatives, the change in the derivatives to the derivative, change from decreasing to increasing. Okay, so you would have an inflection point at x equals 4. So f has inflection points at 2 and 4 because if you just look at the slopes of the tangent lines to the derivative, whenever you have a change in direction of the second derivative, that denotes a change in concavity, okay, as we discussed when we were graphing functions. All right, very good. Rectilinear motion, okay. So recall that if an object has position s equals ft, then the velocity is just the derivative of the function. So the position function is an antiderivative of the velocity function. So likewise, acceleration is the antiderivative of I think they got this backwards. Acceleration is the antiderivative of the velocity function. So if acceleration and the initial values, position and velocity are known, then the position function can be found by anti-differentiating twice. Particle moves in a straight line and has acceleration given by at, which is equal to 6t plus 4. So if we have the initial velocity at -6 and the initial displacement s equals 9, can we find the position function? Sure. We just anti-differentiate acceleration twice. So let's do that. So taking the antiderivative of a of t, we'll get b of t. So the velocity would be the antiderivative of acceleration, which would be 6t squared over 2 plus 4t plus your antidifferentiation constant. And then we take the antiderivative of the velocity function to get the position function. So that would be 6t cubed over 6 plus 4t squared over 2 plus c times t plus d. Okay, and then we plug in our initial condition. So v of 0 was -6. So we can solve for c by plugging in t equals 0. So c is equal to -6. All right, and so make that -6. And this is d, so we can solve for d by plugging in 0. So d would be 9. So make that 9. So there's your position function. Okay. So here to go through the steps. So there's your velocity function. Next will come your position function. Okay, so there's your position, the required position function. Okay, so an object near the surface of the Earth is subjected to gravitational force that produces a downward acceleration denoted by g. For motion close to the ground, we may assume that g is a constant, 9.8 meters per second squared, or 32 feet per second squared. So what can we do with this? A blank slide. Okay. Is that the end? Let me see. Maybe there's no more content here. Okay. Oh, here we go. Just a blank slide. Got it. Okay. So the motion is vertical when we choose the positive direction to be upward. So at time t, the distance above the ground s of t and the velocity b of t is decreasing. So the acceleration must be negative when we move in the upward direction. So a of t is equal to negative 32 feet per second. And that means that you're going upwards. You're fighting gravity. Okay, so taking any derivatives, b of t is equal to negative 32t plus c. And to determine c, we use the information that, say, v sub 0 is equal to 48. So if we have a velocity function of negative 32 plus 48, so my guess is that they went to position. So the maximum height reached is, looks like we skipped a number of slides. So vt. So the maximum height is reached when the velocity, of course, is 0. So you solve t when velocity is equal to 0, you can get the time at which the maximum height is attained. That's when it's 0. Okay, so that would happen when v of t is equal to 0. And let's see, can you get the position? So s prime is equal to v, so anti-differentiate the velocity function. And we get the position function. And so at s equals 0, so at s equals 0, evidently this was data given. So we can solve for d, so the position here. So I think some information was missing here. Okay, so yeah. All right, so you can figure that out based on more concise information. All right, yeah, okay. So I'll leave this to you as an exercise. There'll be some web-assigned questions regarding this example 7, which got kind of truncated in the slides, but I think there may be an example of this in the book. I'm going to leave that to you as an exercise to read. Okay, so now this concludes Chapter 4. So please complete all of your web-assigned questions for Chapter 4 and prepare for your web-assigned Chapter 4 exam as well as your Chapter 4 project, which will be due the first class period after your Chapter 4 exam. And as usual, if you have any questions, see me during my office hour or email me. And don't spend too much time trying to solve a web-assigned question. Again, if you need assistance with a web-assigned question, if it's taking you, like, say, longer than 10 minutes to respond to it, send me an email, request a hint, and I will post a hint on the class website. I will be happy to do so. All right, so that's it for Chapter 4. On to Chapter 5.